let me continue the discussion of topics. One moment, I will need to close this application. I will open. Please wait. So in the first module, we discussed this vector mathematics to pair example at the topic, and second module, as per the syllabus, is process law and Coulomb's law, where they use the governing equations to calculate the electric field due to it. Now, try with the other method, electrostatic potential or scalar electric potential, which already you are familiar with in your higher secondary. Already you had this topic. Now we are going to revisit. And this is a method to calculate, if you know the potential, we can calculate electric field. But compared to the other methods like Coulomb and Gauss's advantages, the reason is the quantity we are going to deal with is a scalar. Potential is scalar and really not involve complex integration, and integrations are compared to Coulomb's approach and easier. Practical application point of view, if you see calculate electric field, if you want Coulomb's law, you need to know the charge distribution. Practically, we are really not aware of. In most cases, we are aware of like, with the charge density, like charge density or surface volume charge density. This is not available. But whereas for in the case of potential, this is available, because potential for potential, you need to know the boundary condition. At the boundary, what is the potential? At the boundary region, you need to know. You need to calculate because it is scalar. Topic what we will discuss today is electric scalar potential. With V, electric scalar potential, or can like it is a potential normal voltage, or this is scalar quantity. Voltage current is there, right? So that is a basic electric quantity. Potential, which is scalar. You need to call it as scalar potential because you have a counter quantity in the magnetic field. To avoid ambiguity, let's potential or voltage. But instead of this voltage, please use this term potential. Now the idea is you want to relate electric field and potential. Potential means this voltage or V, which is known. If potential is known at the boundary, we can get some equations so that we can calculate the electric field from the early approaches. If you know the charge distribution, then you can calculate the charge source is available, then you can calculate electric field. Now we want to relate this. Further discussion, let us first understand the concept of potential. To understand potential, you need to understand work done, because work done per charge will be potential. So first explain what is work done. Let us consider a charge as Qs is a source charge which is kept in the space. This one positive charge is there, so it will exert electric field. Electric field lines will leave from this positive charge. Let us say we are bringing some other to this. Let us say that charge is test charge Qt. Let us assume this that test charge is also a positive charge. So now, if you want to move the test charge from, let us say, this location is and to another location B, you want to move. Let us say I am using this path. I'm taking this path to. The thing is, in the case of electric field exerted by or shown by the source charge QS of that field, we are moving a charge, positive charge QT or test charge from location A to location B.
Sir,
What will happen? Yeah, please.
your voice is low, sir.
1 minute. Hope it is better now.
Yes, sir.
Okay. If it is breaking, let me know. I will change it to other switch to other network. Now, what will happen? You are moving a test positive charge to the toward the source charge. That is also positive charge. So there will be repulsive force. So you need to move the test charge against the some force. Then we can claim it as work done. Work done. So I hope you know the definition for work done. You can claim that work has been done when if you are displacing or locate or you are moving some charge or displacing some charge from point A to point B against the field, against the field. So that's why I'm putting minus. You are doing work against the field. Okay. If you don't understand this example, you think it like the earth and a building. Okay. Let us say this is first floor, this is second floor, this is third floor. Now, if you are moving from ground to first floor or second floor, you will climb like you have done work, right? Because you are doing work against the gravitational force. Gravitational force try to pull you toward this earth, but you are doing work against the gravity, so you can climb. You have done work, or you can call it as a positive work. Suppose if you are jumping from second floor to, or if you're coming down or moving from second floor to first floor to the ground floor, then you can. It's a negative work because the work is not done by you. The work is done by the gravitational force, right? You can say you can releasing the potential energy. Okay? So you need to understand why this negative sign is present here. Now let us continue. We are moving charge, a positive charge QT, test charge from A to B. What will be the work done? What will be the potential between point A and point B? That is what we want to calculate now. The reason for doing all this is we want to express electric field in terms of potential or voltage. That is the reason. Now let us continue. If the relationship force F equal to Q into E, the force exerted by the electric field on the test charge Qt will be equal to Qt multiplied with the applied field. This is the equation already you are aware of. Now you can substitute. So small q or capital Q, anything can use. So F equal to Q into E vector dot dl vector. So work done equal to this charge will be a constant, right? So understand Q is produced, sorry, the E field, electric field is produced by some source charge, which I'm represented here, I marked with red color, right? So Qt is the test charge. So work done equal to negative of, the reason for negative sign, E dot dl vector. You are moving from A to B. Now we got some form like if you move the Q term other side, you'll get work done per charge. Work done per charge is potential. The ratio is known as potential. Work done per charge is known as potential. V will be equal to minus E vector dot dl vector. So this is the equation for potential, or this will be the potential between point A and B. As we have moved a charge from A to B, the potential exists between, or the potential energy between, potential between point A and point B will be, to calculate that, you need to integrate the electric field tangential to the path, dl vector. Okay, so this equation, right from now, we are going to use this equation to calculate electric field. But anyhow, with this equation, if you know electric field, you can calculate the potential because this equation, its integration is involved. So again, we will make it simply. We will modify this form so that we will calculate electric field from the potential. But anyhow, at this moment, you just take this equation V equal to E vector dot dl vector from A to B. Now one thing you need to understand, what about the path? One path I have used some zigzag, not zigzag, some sinusoidal path I have shown here. Now let us consider other path. I started from here, I am going there and I am turning up, then again I am reaching this point. This is, let us say, this is path 2. So early whatever I have shown, that is path 1. You can take even another path, a straight line. I can move, I can start from A and I can travel straight and I can reach point B in a straight line, through a straight line. Now, multiple paths are possible, infinite paths are possible, right? So now, this potential energy or electric field, electrostatic potential or electric field, it is a conservative field. Static electric field is a conservative field. If you don't understand why it is conservative field, it's very easy to understand with this example. Like gravitational energy, you think like this is the ground, this is like a point you want to reach. Now let us say there is some ladder kept and you have started from the ground and you have reached this point 3 using ladder. So this is the path 1. Let us say you have used to reach point 3 or third floor. Now other path, you have walked for some distance in the ground, then you have reached first floor, again you have traveled horizontal to the earth, you have, or in the first floor you have walked, then again you have climbed to the second floor, again you walked in some for some distance in the second floor, again you reach the third floor. Now the green path and red path, whatever the path you took, but ultimately the work done will be same. It is independent of the path taken, because you can climb that you have done work only when if you are doing work against the gravitational field, that negative sign I'm talking about. Okay, so if you are walking parallel to the parallel to the earth means really you are not doing any work against the gravity, so you cannot climb that you have done work. So understand, so in this case, or so that's why we used to call gravitational field as conservative field. Okay, so if it is a conservative field, these conditions, if field is conservative, then the integration, it is independent of the integration path. It is independent of integration path. Okay, so what way you are reaching from A to B, that doesn't matter, but the location matters. Okay, but only the position. So here electric one moment.
Sir, can you tell why negative sign is?
Yeah, I will tell again. See, if I consider this case, this two charge cases, this with marked with QS and QT, right? You just focus only this example. Don't look at the analogy. So usually we can claim work done only when if you done work against some field. See, in this case, these are two positive charges, right? There is a source charge QS which is positive, and U is a test charge. Let us say I am calling you as a test charge. You are also a positive charge. Okay. So what will be the nature? Both are positive. You guys will try to push each other. Okay. There will be a repulsive force. Now you are trying to move toward this source charge. Okay, toward the source charge. Okay, so this is the red color, like this is the force, this is the force, this is the repelling force, and you are displacing dl, or you are displacing, or you are walking against the field. Okay, or you are
Yes.
trying to move toward the source. Okay, that's why that minus sign we are putting. Okay, let us consider other case. Now already this is repelling force exists. Suppose if you are moving in this direction, you are moving away, because already this source is helping you to push, right? It is pushing you away, and
Yes,
again
sir.
you are going in this direction. In that case, you have not done the work. The source charge is helping you to move or push, so that is negative work done. Okay, so that's why um, mathematically while writing, to represent positive work done, in this case the force and the displacement should be in opposite direction. That's why we are inserting this negative sign. Okay,
Okay, sir.
sorry. Okay. So as conservative field, it will be independent of the path taken. Other thing is, if it is independent of the path taken, then the for conservative field, the uh, 1 minute. What will be this? In a closed path, what will be the total work done? You just answer this. In the closed path, what will be the work done? That means you have started from the ground, you have reached start floor. Again, you come back to the ground floor. What will be the total work done? It will be zero,
Zero.
right? Zero. So closed path, the total work done will be zero. Okay, potential will be zero in a closed path. That's why you will never measure the voltage or potential in your circuit in a closed circuit, right? You always across or in open circuit across open points only you will measure the voltage. Okay, only current will flow in the closed circuit, okay, or closed path. That point you need to keep in mind. Okay, so it is as it is a conservative field, in the closed path, total electric field will be zero. Or like in terms of this present discussion, if you start from A, come to point B, again go back to point A. What will happen? From A to B, you are doing the work. From B to A, the charge, like the source charge, is doing the work, but it will be exactly equal and opposite. So it will be zero. Or I can write it mathematically, right? VAB equal to minus VBA. Okay, from move A to B, you have done the work. From B to A, that is negative work done. Why? Because the source charge is pushing you, or it is helping. It only did the work. Okay, so that is negative sign. So the total work done will be work done per charge will be zero, or potential will be zero. So this, I know you guys are aware of this point in the vector mathematics. If it is conservative field, then curl of, I can explain this. If you apply the curl equation, what will you get? Sorry, not curl, Stokes theorem. If you apply the Stokes theorem, you will get del cross E vector dot ds vector, right? This is what the equation if you apply for the closed line integral of E vector dot dl vector. So what will be this? So just now we told a closed line integral of E vector d, or in the closed path, the total work done will be zero. Okay, so from this we can say curl of electric field is zero. So if a field is conservative, curl of the vector will be zero. So this is how we can prove. This is the one point. So 2 points you need to keep, right? One is if it is conservative, then curl of the vector will be zero, and it will be independent of the path of integration. On that point, you can add that in closed path, the total work done will be zero. These 3 points you need to keep it in mind. So from this, you can prove like electrostatic, right here, static electric field is a conservative field. It's very important. Don't blindly write electric field, static electric field. Then condition is going to change for dynamic case. For static case only, we have proved that it's conservative. Okay. So these are some basic discussions. Now let me go back to the equation, what we have discussed, or what the relationship what we found. Potential between A, B equal to E vector dot dl vector. Now, as you know, the source of electric field is Qs, right? Qs is the source of electric field. Then what is the electric field? Now let us replace this E vector equation in terms of the source charge. Okay? Electric field due to point charge. Because to solve the problem, we need to expand this, right? So E vector is equal to Q over 4 pi epsilon naught or cap by R square. Now, so if you substitute, you will get what is QQS, okay? QS, that's the source of electric field, right? So always put in suffix qt or qs, so that some point of time you will get in confusion what that q means, because sometimes two terms will be together. You need to identify which is source, which is the test charge. So it's a good habit always to keep the detail along with the charge. Now you need to do dot product with dl vector. Now what is dl vector? In which coordinate system this equation is? This whatever the electric field equation I wrote for a point charge. This is in rectangular, Cartesian, spherical or cylindrical. Which coordinate system? Now you guys need to replace dl vector. You need to first know.
Spherical.
Good. It is in the spherical Good. It is in the spherical coordinate system because r term is there, right? And for point charge, why we prefer to take the spherical coordinate system? Because there is a spherical symmetry exists. The electric field from a point charge will leave in all directions. 360 directions it will go. So dl vector will be dr into ar cap. So this is what again important point for the just 1 minute. One moment, yeah, this point. It is independent of the path taken, I told you earlier, right? Now let us try to understand with in terms of this equation. So you can see it is independent of theta and phi, correct? Because the electric field from the source is going radially. So you need to bother only about the radial direction or the point, like starting point and ending point. It is independent of the theta and phi. Whether you are going in zigzag path or if you take whatever the path, that doesn't matter. It's not going to influence on how much work you've done. So it's only decided by the shortest path what will be the best path. The path will be like shortest path between the 2 points, or you can say radial. Radially, if you connect 2 points, that will be the shortest path. Okay, here in this case, I have drawn in the green color. Okay, if you don't understand this theta and phi, leave it. Anyhow, please understand we are not doing integration in terms like with respect to theta and phi. That is reason is it is independent of theta and phi. Okay, theta and phi means like you are staying in the same floor. If you are walking circularly in the same floor, really you are not done any work. Okay, now if you reduce this equation, qs over 4 pi epsilon naught is the constant. So integral dr by r square, uh, limit from a to b. How much is this? Integral r power minus 2 into dr. Sorry, I think already a negative sign is there, right? I have ignored the negative sign, so don't forget. You just insert the negative sign. So minus q over 4 pi epsilon naught. So integral r power minus 2 into dr will be r power minus 2 plus 1. Okay, r power minus 1 over minus 1 from a to b. So this minus minus will get cancelled. You will get qs over 4 pi epsilon naught 1 over rb or minus 1 over ra. What is this ra and rb? See, while solving the problem, you can easily substitute this q as everything. But most difficult part in this, not difficult, tricky part in this problem, especially with this potential problem solving, will be the r. What is r? Ra and rb. Now, instead of going there, I will draw a picture here. Now, let us say this is starting point A, from like where you are moving the test charge and you are reaching the point B. Okay, let us say this is the path you are taking, and there should be some origin, right? With respect to origin only, you can draw this r. What is r? R we used to use, like we used to call it as position vector. Okay, so position vector drawn from the origin is r. Okay, this is ra and this is rb. So this is origin. Now the question is, where is the source? Where is the source? Source we assume it is at the origin. QS is at the origin. Okay, it can anywhere, but like in this case, we assume the source is at the origin. So we will get a simplified equation. Is clear? It is like you can see it clearly here. It is you can say VAB equal to VB minus VA. End potential minus starting potential. Okay, we know end potential may be less or more than that of the source potential starting point, but generally we used to write like this. Like VAB means is a starting point, or just like a reference. You have started from here, and you have, this is the end point you have reached. Okay, so the total potential will be equal to the end potential minus the starting potential. Don't go with the convention like higher potential minus lower potential. Here we can't say whether we are at the higher or lower. That's difficult to say. So always go with this convention. N VB minus VA, or N minus the starting like reference potential. You can go with this equation. Okay, so in this case, try to understand R is the radial distance. See, this is scalar, this is not vector. Actually this is vector, but that is a scalar, and potential is a scalar that you guys well aware of, because circuit, this is a circuit theory. Whatever the voltage you are using, the same voltage equation is this. Voltage term is this equation, is present in this equation. So it's a scalar, it is not at all a vector. So don't put this as a vector. I know several students used to do the mistake. They used to put a vector equation here, and they used to write the express the final answer as a vector equation. That's not correct. And in this equation, one important note is source is at origin 0 0 0. That is first note. Second note is the reference potential is given. Reference potential means, which is the reference point? This is the reference point. In the earth gravitation, earth, like in this example, earth gravity analogy, whatever I have discussed, what is the reference for all of us? Like we used to take ground as a reference, right? With respect to ground, you are rise to first floor, you are rise to second floor, you have reached up to third floor, right? So reference potential is very important. If reference potential is not given, you can assume, if that's what I'm going to simplify this equation. Let us say this equation this is a general equation A. Now we will simplify this equation A with this condition. Suppose the reference is not given, like it is not given, like from where you have started. Okay, where we have started. What will you do if reference potential is not given in the problem? What will you do? You can simplify this. If reference is not given, that mean like you have not provided the information that from where you have started. Okay, so only I am aware of that you have reached this point B, but I don't know from where you have started. If such information is not available, I will assume that the reference potential is 0. That means you have started from infinity. You have started at a point infinity where it is 0 potential. Okay. So if it is not given, we will assume reference potential is 0, VA equal to 0. When VA will be 0, that means when RA equal to 1 by RA equal to 0. When it will be 0, sorry, this term should be equal to 0. It will happen only when RA is equal to infinity. If you have started at a distance or location at infinity and you have reached a point B, in that case, we can assume that the reference potential, or the place where you have started, right, at that point, the potential is 0. If you don't understand this, very simple. Let us say you have reached, now you are present in the 5th floor, reached 5th floor. Nobody is going to ask from where you have started or how much work you have done. Obviously, maybe today or yesterday you have somehow you need to be started at from ground floor, right? You may stay at first floor or second floor for some time. That doesn't matter. But the potential energy will be decided or with respect to the ground. Okay, from ground, with respect to ground, you are in the 5th floor. So if you jump from the 5th floor, then you will release all that energy, and you can enjoy. Okay, so that's what I want to say. So now we can simplify this equation. Potential equal to Qs over 4 pi epsilon naught into 1 over RB. Or you can simply write, as the source is not given, you can write this equation like V equal to Q over 4 pi epsilon naught into R. That's all. So what is the difference between equation A and B? We can use equation A only when the reference potential is given. If the reference potential is not given, you can use equation B. And R is a distance between source charge, and test charge wherever you are. Okay, that will give you the R or the distance. Any questions? Try to see the difference between electric field and electric scalar potential. In electric field, the formula is Q over 4 pi epsilon naught R square. Here you can see over R. So what do you understand from this? Just compare these two equations, equation B and C. See the difference between electric field and potential. Only difference is the denominator. Here it is the field decreased with 1 over R, but here is inverse square law. The electric field obeys inverse square law, but where in this case it is inverse of R. Okay, so mean electric field will die off faster than the potential. Likewise, shortly in dipole, you will come across a term 1 over R cube. Okay, so you need to, like, everything else will be same, only in the denominator, the term R, which is the radial distance from the source, you can understand the nature of the field. So here you can see the electric field will die at fast rate compared to the potential. That's what you need to understand from this. Thank you. Yesterday, you guys have responded, submitted, forwarded the form. Shortly, we'll get some notification, maybe for further discussions, like for interview or something. We will get some notification from the EMC Society Student Branch chapter. Any questions? Now let us take one simple example. Is in the short time I can't, because one more two examples I want, only one example I thought of solving, but today I can't take that example. It will take time to complete. I will take very simple example. See, this, if you look at equation A and B, it sounds simple, right? Sounds very simple, but problem is this term R will make all the confusions during especially at the exam time. Now will be happily, you can may think this is very easy to solve and get the mark, but it is not going to happen when you solve the problems really. Okay? Because when I will give multiple sources, sources means like a point source, a line source, or surface source will be there, and you need to calculate the potential between 2 points, and the reference potential will be given, everything will be given. At that time, only the term which is going to create trouble is this R term. Okay. Now, I'll give one simple example. I think to solve the example, I don't really much time. Maybe in continuation to this, I will discuss one more topic, and then I will move to that example. So far, we had this equation, electric scalar potential is integral of open line integral of E vector dot dl vector. If you integrate the electric field along the or tangential to the path, then you will get the potential. A simple way to understand this is in terms of units. It's very easy. What is the unit for electric field? It is volts per meter. The unit for dl will be meter. So you can see this meter and meter will get cancelled, and you will get the unit for the voltage, that is volts. It is dimensionally, it is you can easily understand, right? Our future, you can easily recall like how to write the if you want potential, then you need to integrate E vector, and you know this is volt per meter, this is volt, then you need to multiply with meter or length, right? dl should be there. It should not be ds or dv. That's what I want to convey here. Okay, and here you want scalar, so you need to put dot product. So in this way you can reconstruct the equation without memorizing these equations. Now the point is, we want to this is the integral form, where still the problem with this equation is it is not usable, right? Because unless you know the electric field, you can't calculate the sorry, if you know the electric field, you can calculate potential, but if you know the potential, you can't calculate electric field, because this is trapped in the integral form. You need to bring it out. Okay, that's what we will do it now. So you can say like dv equal to E dot dl, right? E dot dl. Or you can say dv equal to if you take dot product, E into dl. You can say dv by dl equal to negative of E. What is DL? DL can be, if you take a cylindrical coordinate system, it may be d rho, right? If it is a spherical coordinate system, it may d r plus d phi d theta. If it is a Cartesian coordinate system, it may be dx dy. Okay? The meaning is like the displacement may have displacement. See, if this is a displacement from A to B, this happen only along the x direction dx. If this is way, if displacement happen from A to C like this, then it is dy. That's all. Okay. So you can write it as a general equation, general vector equation. Like this derivation not matters, and there is no derivation for this. E vector is equal to negative gradient of v. Because gradient is dou by dou x. Okay. So gradient of v would be dou v by dou x, or change of potential along x direction plus change of potential along y direction plus change of potential along z direction. That's all. Okay, so we can write this equation like this. Now we got an equation where we can calculate electric field when potential is given, or charge electric scalar potential is given. So this equation v equal to negative e dot dl, right? So this in integral form, and the same equation if expressed in the differential form, this is the differential version. E vector is negative gradient of v, and hope you know, compared to the integral versions, differential versions, you will get more physical insight into the equation. That is the advantage of the differential equations compared to the integral. And again, mathematically, it is really quite easy to use the integral, this kind of differential form rather than the integral form. Okay. So now with this equation, you can calculate electric field. Now let us try to understand the meaning of this E vector equal to negative gradient of V. Already you guys were introduced this about, and we have solved a lot of problems in your school level. But anyhow, only difference what we are making at this semester is only we are simplifying the subject by fitting the problem in cylindrical and spherical coordination. That is the only thing we are doing. Now let's try to understand the meaning of this equation. How will you read this? Electric field is equal to negative gradient of the potential. It's very easy to understand this concept. Now let us say this is the electric field. There is a source charge Qs, as this is a positive charge. Let me consider only one force line. Like in the horizontal direction, it will exert force in this direction. Now I'm moving a test charge from point A to point B in this direction, opposite direction. Let's say the test charge is a positive charge. Now if I move from A to B, then I can climb like I have done work. Hope you agree with that. Okay, now the point is, what is the potential at A and what will be the potential at B, which is at higher potential. I'm not asking what is the value of potential at A. Okay, maybe 0, or maybe some initial value may be there. Now let us not bother about it. Now the question is, which is correct, whether VA is greater than VB or VB is greater than VA, which is correct? At location A, what will be like, now you have moved away from point A to point B, or if you are moving, you are doing work against the field, okay, which is marked with black color. Okay, and this test charge is moved from point A to B against the field, applied field. And then you can climb, work done, right? Work done. Now the question is, which is correct? Out of which is correct? VA is greater than VB, or VB is where the potential will be more?
Sir, VB will be greater than
Good. That's correct. Obviously, that is correct, right? See, like first floor, second floor, third floor, the same case you take. Okay, it is like A, it is like B. If you move from point A to point B, you are acquiring more potential energy. If you jump from point floor 1, first floor, you jump from floor 3. Okay, where you will release more energy? At obviously from third floor, because you have acquired the potential energy by doing work against the gravitational force. Obviously that is correct, right? So now this is correct. This is not correct. So you can see electric. Now I will write the details here. Here you can see here this is point A has lower potential and point B has higher potential, right? Point B is at higher potential as charge is moved from point A to point B. Now you can say electric field is in this direction. Let us say this is positive x direction. But what about the potential direction? Potential is, see, just to answer, electric field is opposite to that of the increase in potential, correct? The potential is increasing in this direction. In the minus x direction, potential is increasing, but electric field is in the positive x direction. Okay, that's why electric field will be in the opposite to that of the increase in potential. Increase in potential is in the minus x direction, right? So both are in opposite direction. That's why this minus sign came. That's the meaning of that equation, E equal to negative gradient of V. Any clarification required on this?
Yes, sir. So how do we decide which one is higher and which one is lower?
Yeah, right. See, why, like how we are deciding is again same. You may take the gravitational example, or see, when we can claim you have done the work. If you done the work against the field, applied field, then you are acquiring more potential energy. You have started from point A and you are moving against the applied field. Okay, so as you are moving point by point toward, you are moving away from point B, sorry, point A, you are slowly acquiring the energy, right? So as you reach point B, or it is like first floor. This is like third floor. Okay, so this is the field, like whatever the black line I'm showing, that is the gravitational field, gravitational force. Okay, you are doing the work against the gravity. From floor 1 to 2, you are acquiring some, you will gather some, or you will retain some potential energy. From moving from further, like let us say from 1 to 4 or 1 to 5 or 1 to 6, you will gain more energy, right? As you are moving to higher the floor, you will have more potential energy. Higher the better the, or higher the potential energy. Is it clear? So that will happen only when if you are moving against the applied field.
Yes, sir. Okay, sir.
Right? That's why this is applicable only when this story applicable only when if you are moving against the applied field. So in this case, I think this I didn't included this point. So this is a positive charge. Source charge is a positive charge. This test charge is a positive charge. So nature will be both will try to repel each other. They will repel each other. Okay, there will be repulsive force. It is like two repelling magnet. Two magnets we have, they are repel. Now, if you want to bring the other magnet close to the source magnet, what will happen? You need to spend some energy. Okay, you need to push. But the moment you release, if you move your hand, what will happen? The magnet will release that, like because you are releasing the energy. Okay, it will come back to the original position. It's the same story.
Okay, sir.
Okay. See, guys, like you have freedom to ask questions. Also, you can have freedom to give answers. See, sometimes whatever analogy I gave may not be exactly fit to these examples. You may have some better example. Really, I welcome you guys to share some other like analogies or even better explanation if possible. Please give. Okay. Um, so So now we can use the equation, second equation, to calculate electric field from the potential. And as the source is a scalar only, it is going to be nearly what this mathematics involve. You are multiplying a scalar with vector. So that is such a simple mathematics, right? In vector, that is compared to your curl and gradient. Sorry, curl and divergence. Gradient is one of the simple operation because you are multiplying a scalar with a vector. So that way, this method is advantage, and the other way, as I told earlier, compared to the source charges, here you need only information about the potential at the boundaries. So it's somehow practically a known detail. So this is practically we can use this equation to calculate electric field due to the potential. That is we can use. Now, as we discussed early, what will be this? If you take closed path, the total work done will be equal to 0. Equal to 0. If you apply the Stokes theorem, then you will get curl of E vector will be equal to 0. So this equation is one of Maxwell's equation. These two equations, curl of E vector under static, is only applicable under the static electric field. When we move to further modules, like while we are discussing the dynamic case, if the field is varying with respect to time, this is not true. Curl of electric field will not be 0. Okay, that we will discuss it later. So these 4 equations, what you need for further discussions. Maybe that simple example I told, that's not possible to discuss now. Yeah, let me just open the slide and you can have a look at it. We don't need to solve that, just go through and you'll get like idea of what kind of problem you will get. I have not completed the papers. Once the checking is done, I will let you know. Then you can check the Code Tantra website. So until then, don't please check.
Okay, sir.
Oh, sorry, that example I have not included. Wait. Anyhow, I will open the textbook and I will show that example. Now hope this is visible. We are getting the some example. I'm shared some example. It's visible to you. Okay. See, I will take just 1 minute to complete this. So 2 point charges QS. Let us say this is a charge source 1 of -4 microcoulomb. And sorry guys, it's already 9:50. I will continue this in the next class. So download the attendance. You may leave. If there is no questions, you may leave. I will continue this.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.